To begin our next unit, we're going to do a little bit of a review of powers. Back in your grade 9 academic program, you studied powers and you looked at the different power laws that could be used to simplify powers and exponents. I'd like us to start with a bit of a skill review, and I've given you 3 different questions that I would like you to try to evaluate. So take a moment now and copy these down and see if you're going to get the final answer. So pause the video, try to complete these, and then check back when you've had a chance to attempt them. Now that you've had a chance to attempt the questions, have a look at my answers and compare to what you have put there. Hopefully you got them all right. Even if you did get them all right, there are some other things that I'd like you to consider. For the second 2 questions, I need you to consider why things are the way they are. Why 10 to the exponent 0 will give us a value of 1, and why 2 to the negative 1 can be rewritten as 1 over 2. If you take a look at your calculator and actually try to enter 2 to the negative 1, you'll find that you get 0.5 as your answer, which is equivalent to the fractional expression of 1/2. So as we move through the lesson, we'll discover why this is actually the case. I want you to start by thinking about it on your own and seeing if you can follow our train of thought later. I'd like to start with the power law for multiplication of 2 powers. Notice that we have a to the x and a to the y that are multiplied together. So these 2 powers that are multiplied, we also notice that they share the same base. So hopefully we can recall from what we did in grade 9 that when we're multiplying 2 powers with the same base, we add the exponents that we have, and that will give us a more efficient and concise way to write our answers. So there's the general form that we would have for that. If we wanted to consider a numerical example that might help us to make sense of this, I could consider the powers 2 cubed and 2 to the exponent 4. If I wanted to, I could then write these 2 powers out in expanded form. So 2 cubed is just 2 multiplied by itself 3 times. 2 to the 4 is, of course, 2 multiplied by itself 4 times. Instead of rewriting that now as 2 times 2 times 2 with our calculator, we can notice that there are 1, 2, 3, 4, 5, 6, 7 2's that are multiplied there. So we could rewrite that as 2 to the exponent 7 as a simplified form. Notice that we would get the exact same answer of this if we notice that the 2 powers had the same base of 2 and we added the exponents to the 3 plus 4 equals 2 to the 7. So that's a nice numerical way to confirm what we've stated up here as we've written our power law. Let's move on to the law for division of powers now. Here are 2 powers written in general form using variables, a to the x divided by a to the y. When we multiply 2 powers with the same base, we added exponents. When we divide 2 powers with the same base, we would subtract the exponents. So the general form of that would be a to the x minus y. Once again, to make sense of this, we can look at some numerical examples. I'm going to consider the power 3 to the 4 divided by the power 3 squared. If I want to, once again, I can write it out in expanded form. 3 multiplied by itself, 4 times, and 3 multiplied by itself twice. If we want to simplify this expression, I'll notice that 3 divided by 3 gives us 1. Another pair of 3's can divide away to give us 1. So our final answer could be written as 3 squared, or 9. If we want to use the power rule that we have here for division of powers, we said that since the bases are the same, so that since it's both base 3 and we're dividing, we could subtract exponents, 4 minus 2, which gives us 3 squared. Notice that this power law just helps us get to the final simplified form as a single power a little bit quicker than the other way. Let's move on to the power law for multiplication. Rather than multiplication, I should have said taking the power of a power. Notice that in this situation, we have our exponents that are separated by brackets. In this situation, we multiply our exponents. So this would be simplified to x times y. Let's look at a numerical example to try to help us make sense of this. So I've got 5 squared cubed. Let's consider that example. So I've got 5 squared that we're multiplying by itself 3 times. So I'll say 5 squared times 5 squared times 5 squared. Then using our power rule for multiplication, since each of these powers have the same base, we can add our exponents. So 5 to the 2 plus 2 plus 2, which is 5 to the 6. Now we could, if we wanted to, change that with our calculator and evaluate it as a number. Right now our answer is written as a power with a single base. Notice that if we use the rule for taking the power of a power that we've generalized up here, 5 squared cubed, I would multiply the exponents, 5 to the 2 times 3, which would still give us 5 to the 6, which is the answer that we came upon using the expanded form. Now that you've had a little bit of a chance to think about the negative exponents that I showed you on the first slide, I'd like us to consider this situation a little bit more carefully. So let's start using the power rule for division. Notice that our two powers have the same base. They're both base 2. And when we're dividing two powers with the same base, our rule told us that we could subtract exponents. So I could rewrite this as 2 to the 2 minus 5, which is 2 to the negative 3. A lot of us will say, well, that's great, but does it really make sense to me in terms of what the number actually means? A way to try to make sense of it is to actually take the same question and to do it slightly differently. So we're going to do the same question, we're going to follow mathematical principles so we're not making any errors, and our answer then that we get over here should be equivalent to what we got using our rules for dividing powers over here. So 2 squared is 2 times 2. In the denominator, 2 times 2 times 2 times 2 times 2, 2 multiplied by itself 5 times. Let's divide away some common factors. 2 divides by itself, leaves us with 1. Another 2 divided by 2 leaves us with 1. So we'll notice that the final form here is we have 1 over 2 times 2 times 2. That's what we're left with. We could also write that as 1 over 2 cubed. So we've done the same question two different ways, and we got two slightly different presentations of our answer. So it should follow then, by reasoning, that if we did the same question, we used appropriate mathematical procedure, that these two solutions would be equivalent. And basically they are. So another way that 2 to the negative 3 can be written so that it no longer has a negative exponent is 1 over 2 to the positive 3. If we want to generalize this a little bit, I could say that any value, so I'm going to call my base b, if I had to the negative n, I could simply write that as 1 over b, and we change that exponent to a positive n. In this case, of course, I'm not allowed to have my base being equal to 0 because it's part of the denominator in an expression, and we all know what happens when that occurs. Here are a few other ones that I want you guys to try. Write down the 3 questions that I've given you. I would like you to take these powers and rewrite them as powers having positive exponents. Pause the video and give it a try now. Hopefully we were all able to see that we could simply rewrite them by taking and putting the power in the denominator and changing the exponent to a positive value. One last thing I would like you to consider here is what happens when we have a situation like this. So what about 4 over 5 to the negative 2? I would like you guys to try to rewrite that so that it has a power having a positive exponent as well. I would like us to think about this in terms of our long mathematics and the mechanics of it, and then I would like you to see if you can spot a bit of a shortcut that you can use to help with this. So if we want to start and work on this in the exact same way that we've handled the other questions, we know that we need to take and put our power in the denominator. So 4 over 5 to the negative 2 will become 1 over 4 over 5 to the positive 2. We can change this up a little bit if we want to. We could rewrite this as 1 over 4 squared over 5 squared. And then hopefully we can see that another way we could express this division that's implied by this large line here would be to write it so that we were horizontally writing our division. So 1 divided by 4 squared over 5 squared. Sometimes writing it like this makes it easier to see the next step. When we're dividing by a fraction, we'll remember that we multiply by the reciprocal, so we end up getting 1 times 5 squared over 4 squared, which basically we could write as 5 over 4 all squared. Of course, that would be 25 over 16 if we wanted to go there. What I'm interested in you seeing is the connection between 4 over 5 to the negative 2 and 5 over 4 to the positive 2. So if we were to try this a couple more times, we could see that in general, if we have a fractional base, so a over b to the negative n, we could rewrite that as b over a to the positive n. It's a little bit of a shortcut. I do want you definitely to understand why this is working and this process that's contained here, but this certainly is a nice shortcut that we can use. The last thing that I want us to consider is the idea of zero exponents. We looked at this at the first slide as well. Let's do this in two ways too, so we can try to make sense of what we're getting as our answer. Let's start by using the division rule for powers. Notice that we have the same base in the example that I've created here. When we get the same base and we're dividing, we know that we can subtract the exponents. So notice we get here 2 cubed over 2 cubed, which is 2 to the 3 minus 3, which is 2 to the 0, which for a lot of us doesn't make all that much sense. In an effort to try to make sense of it, let's take 2 cubed over 2 cubed, and let's expand it. So we have 2 times 2 times 2, all over 2 times 2 times 2. In this case, we could divide our 2's away, or we could actually work it out and get 8 over 8, but regardless of how we do it, we're always going to get 1. So we've done the question in two different ways. We got 2 to the exponent 0 as one expression of the simplified form, and we got 1 as the expression of the simplified form when we did it by expansion. Basically what this tells us, if we have anything at all that's raised to the exponent 0, we're going to get 1 as our answer. I chose to have 2 as the base here, and I chose 3 as my exponent, but really as long as I have the same base and the same exponent, we're always going to get some sort of power that has an exponent 0, and if we were to expand that, we would always get 1 as the final form. I'd like you to take the rest of the day today to work on some practice problems. These could be class practice problems, I guess, instead of home practice. Nonetheless, I'd like you to try them all before we come back. Sorry, my stylus is making my messy writing even messier. That says a 5 odd here. I've tried to choose questions that will help you to reinforce these ideas. When I say odd, I mean the first, the third, fifth question in that little question. So I've tried to cut it down by only assigning half of 4, 5, 6, 7, 8, and 13. It is important. There should be very quick questions, so to speak, and we should be able to do them very quickly, but creating a sense of ease with this work is definitely going to help you as we move on. Questions on page 223, number 16 and 18 are also ones that will help us to review these grade 9 concepts, so we'll be all set to go with our grade 11 stuff next. Have a great day, everybody. Bye-bye.